We all know that large language models generate text through the next token prediction mechanism. Specifically, given a prompt and an LLM, we follow these steps to generate the output. First, we feed the prompt into the LLM. The LLM performs a forward pass and outputs a probability distribution for the next token. Then, we sample a token from this distribution. This token is subsequently added to the end of the prompt to complete one generation step. Then, we repeat the process several times to generate the full sequence. A natural idea to improve generation quality is we can use multiple LLMs. At each step, each LLM separately performs a forward pass. Then we combine their results to get a better prediction distribution. In our work, we call this kind of method collaborative decoding. There are many ways to combine the results. Next, we introduce 3 common examples. The first method is model ensembling. It combines information from multiple LLMs by averaging their output distributions. The second type is contrastive decoding. It uses a large and a small LLM, subtracting the smaller one's output from the larger one to reduce hallucinations and improve quality. The third type is decoding-time realignment. It combines the longits of a human-aligned LLM and an unaligned one to adjust the level of alignment flexibly. However, this kind of method faces an efficiency challenge. Specifically, as you can see, at each step, the LLMs are usually invoked sequentially. This means generating one token needs 3 forward passes, making it 3 times slower. Now you might ask, why not run them in parallel? That is, feed the prefix to all 3 LLMs and run forward passes at the same time. That's a good idea, but in practice, due to communication delays between GPUs, this parallel setup can be even slower than the sequential one. This brings up a question: can we accelerate collaborative decoding without sacrificing its quality? We propose collaborative decoding via speculation to address this challenge. This approach is inspired by speculative decoding, so let's first explain how that works. Speculative decoding uses a smaller proposal model to speed up the target LLM's inference while preserving output quality. It starts by using the proposal model to quickly generate 4 tokens as a guess. Next, the target model is invoked to compute the distributions of these 4 tokens in parallel. These distributions are then used to verify the guesses. Through the verification, some tokens are accepted, while others are rejected. Here, we assume 3 out of the 4 tokens are accepted. These accepted tokens are added to the prompt for the next round. The verification step ensures that accepted tokens strictly follow the target model's distribution, making speculative decoding a lossless acceleration technique. In this case, we generate 3 tokens, using 4 invocations to the proposal model and just 1 invocation to the target model. Since the proposal model is lightweight and fast, speculative decoding achieves about 3 times efficiency. There is a special phenomenon in speculative decoding. During verification, if all 4 guess tokens are accepted, the target model produces an additional token. We call this the bonus token. The bonus token's origin relates to how transformer-based models predict the next token. When an LLM performs a forward pass, the output at position I predicts the token at position I plus 1. This means the probabilities for the 4 guessed tokens are from the 5th to the 2nd to last outputs. The very last output predicts the next token. So, when all guessed tokens are accepted, we can naturally sample an additional token from this final distribution. Next, we introduced the proposed method Collaborative Decoding via Speculation, or CoS for short. CoS makes two improvements on speculative decoding. First, during verification, we use the combined distribution instead of a single model's distribution. Specifically, we first invoke the proposal model 4 times to generate 4 guess tokens. Then, we invoke the large model once to compute 5 distributions in parallel. As mentioned before, the 5th distribution is used to produce a bonus token. For verification, we first combine the distributions from the proposal and target models. Then, we use the combined distribution to verify the guess tokens. Through this process, the generated tokens follow the combined distribution. This allows us to extend the speed-up principle of speculative decoding to the collaborative decoding scenario. Specifically, if we want 2 models to collaborate, we can treat one as the proposal model and the other as the target model, and apply speculative decoding with combined distribution for verification. This gives us an accelerated version of collaborative decoding, which we call naive CoS. The second improvement is the alternate proposal framework, which extends naive CoS and further speeds up inference. Let's explain this framework with an example. First, LM1 performs a forward pass to generate a guessed token. Then, we invoke LM2 to generate 2 distributions, one to evaluate the guess token and one for a bonus token. Next, we use the combined distribution to verify the guess token. And sample a new bonus token from LLM2's last distribution. Then we invoke LM1 to verify LLM2's bonus token. After that, we use LLM2 to verify LLM1's bonus token. In summary, each model invocation verifies the other's bonus token, and each verification yields a new bonus token. This creates an alternating guessing process between the 2 models. So we call this the alternate proposal framework. In standard collaborative decoding, each LLM invocation can generate only 1 tokens. But as you can see, with this framework, if all tokens are accepted, each invocation produces 2 tokens, which doubles the efficiency. In this example, to better explain our framework, we assume all tokens are accepted, and each model is invoked equally. However, you'll see a more general example later. The proposed opus can also extend to scenarios with more models. Here, we demonstrate CoS with 3 models. In this case, we still assume all tokens are accepted, and each model is invoked equally. Finally, we provide a more general example. In this example, the number of invocations to each model is not equal. To maximize speed, smaller models are invoked more frequently. Additionally, we show how CoS discards guessed tokens when a rejection occurs.